All right, welcome to our first part of Chapter 10's discussion, where we're going to start talking about behavior and properties of gases. There will be a second part that we'll have early next week as well that'll kind of wrap up the chapter and some of the more theoretical aspects at kind of the molecular level. But really, this first half is going to be more focused on kind of some of the calculation-based kind of relationships that we see for various properties of gases that we often talk about. So, as a starting point, really this whole chapter is all about really kind of basically gases as a whole as a physical state. So, as kind of a quick definition, we define gases as collections of particles that just move randomly throughout the volume that they occupy. And really, this means there's nothing kind of holding those particles together. So, all of those particles moving about are not only moving randomly, but are not really attached to one another. And so, you have kind of these individual particles of gas that might be individual elements. They might be individual molecules. Just kind of depends what you actually have. But everything's being able to move freely, and really there's not a fixed shape to a gas, right? They take up whatever shape or volume really that they're allowed. And one of the things, and probably one of the more prominent properties that we'll typically talk about for gases is going to be pressure. And I want to spend a little bit of time talking about this in particular because it's not really a measurement or a unit that we've talked about yet this semester. It might have gotten introduced very, very briefly at the start of the semester, but we really didn't do much with it then. So we're going to come back and talk about it a little bit more right now. So what pressure is, or what creates it anyway, pressure is really kind of the measurement that takes into account all of the collisions of moving particles with the walls of their container. And when those collisions happen, there's a force that those collisions basically kind of exert on the surface of the container where that collision occurs. And so if we add up really the sum of all of the forces of all of the collisions happening on the surface of a container for all of the surfaces basically of that container, we're able to then calculate what we call this pressure for a gas. Because that gas it's exerting this force over like an area, which is the surface area of your container, that's constantly pushing on that container outward, and that's what we refer to then as this pressure for a gas. And giving kind of a visual image of this, all of these little particles that are moving around in this box, as they bounce off the walls of the container, that's what's really creating our pressure. Right, and so over here we see like the actual kind of the paths of things and how they're colliding and bouncing off the walls of the container. That's what's creating this pressure that we talk about. Now, units, because there's actually probably more units for pressure that you'll see than there are units for any other particular measurement that we've probably really run into this semester. And so I do want to talk about kind of all of the ones that are relevant that come up pretty often so that we're kind of just aware of what they are. I'll give some conversion factors for them. Probably more often than not, you're going to be given those conversion factors on tests if you ever need them both now and in the future, just because it's not expected for you to memorize all of the conversion factors. That said, a couple of them are probably useful things to know, and we'll kind of note those as we see them. So the first unit is something called the Pascal. So its actual kind of normal symbol is capital P, lowercase a. This is the official SI unit for pressure, but the reality is we don't really use this unit very often. And so what I'm going to give for each of these other unit types of pressure that I'm going to introduce here, I'm also going to give what is the value of atmospheric pressure in those units. And so for pascals, a pascal is actually a really, really tiny amount. It's 1 Newton of force over a full square meter of area. A square meter of area is huge. 1 Newton of force is really tiny. So to get to atmospheric pressure, it's a really big number. This is 101.3 kilopascals to get to atmospheric pressure. And because this unit number is really big to be kind of a standard atmospheric pressure, I think it's part of the reason we see a bunch of other units that are often used and why this one's not as commonly used, even in equations that we see regarding pressure. So our other units that are probably going to be a little bit more common, from strictly a measurement standpoint, millimeters of mercury, even though it looks like a length, is actually a measurement of pressure. And millimeters of mercury is also the same thing as something called torr. So if you see either of those two units, they are identical to each other. And in general, atmospheric pressure is what we call 760 millimeters of mercury. And I'm going to talk about something called barometers as far as ways to measure pressure in a moment. And from kind of our oldest versions of barometers that I'll show and demonstrate, that'll give you kind of an idea of where this millimeters of mercury measurement actually comes from. But that is a pretty common unit that you will see pop up pretty frequently for pressures. Now, other units of pressure, the one we're probably going to use the most often for calculations is going to be this one. It's atmospheres. So atmospheric pressure is really easy. right? Atmospheres as a unit of pressure was defined so that whatever, basically your standard atmospheric pressure, that's 1 atmosphere of pressure. And so it's kind of standardized to what our current atmospheric pressure is. And even though it's not the official SI unit, it is the one that will, one that will probably show up the most in the calculations that we're going to be doing regarding pressure and things with gas laws in this chapter. Some other ones that are a little bit less common. If you're a physical chemist, which there's not usually many of them, but those that are, they do end up often using something called the bar instead of atmospheres, and for a lot of different calculations, where 1 bar is exactly 100,000 pascals. And remember up here we said it's 101.3 kilopascals is 101,300 pascals. So 1 bar is actually really close to atmospheric pressure, but this at least keeps things kind of to a more standardized version of pascals, which is the base SI unit of pressure. And so it keeps things a little bit more standardized for SI unit standpoint, or from an SI unit standpoint. So you do see the bar sometimes get used in some different things. Usually in physical chemistry, for anything for general chemistry, we're probably going to use atmospheric pressure, just like, or atmospheres probably is the most common unit for almost everything. Now, there's one other pressure unit that's probably pretty common to a lot of you from kind of an everyday life sense. If you ever had to fill up your tires with pressure, for instance, or put pressure in your tires, you've probably seen a unit that was labeled PSI, which stands for pounds per square inch. So this is also another very common unit. Atmospheric pressure is about 14.7 PSI. So you see your tires, most cars are often like 30 to anywhere, maybe 30 to 40 PSI is kind of the rating of where do you want the pressure in those tires to be. And so that gives you kind of an idea as far as what the pressure inside of them actually is, right? As far as kind of compared to atmospheric pressure in these. Now, a lot of times there's some other factors involved with things what's called the gauge pressures. We'll probably, if we could talk about that, probably talk about that in the second part of this lecture. But that is something that can sometimes come up when we're measuring these things. And so just to kind of summarize general conversions, the unit we'll probably use the most is right here, atmospheres. And these are kind of the conversions that if you know them, it's nice, but more often than not, if we need them, we're probably going to be given the conversions. PSI is the one I might say you might want to just recognize just because it's one that maybe applies to your everyday life more than others. Millimeters of mercury might be the more common one that we're converting back and forth with atmospheres for, because millimeters of mercury and torr do show up frequently in a bunch of the different problems that we see involving gas pressures, both this semester and in the future in 1212. All right, so measuring pressure, and this is to give you an idea really of kind of where millimeters of mercury first originated from, and why that's kind of often used as a unit of pressure, even though when you see like millimeters, that's a length unit, right? So how this works, pressure was first measured in what we call mercury barometers. We have barometers today that also measure pressure that are usually set up a little bit differently. When we're able to get back to Rogers, if you're able to go through into the 1211 lab, if you look on the door in room 211, there's actually kind of a really old school mercury barometer kind of set up there. And you can actually read the pressure off of it, although I think it's vacuum sealed. Probably not perfect anymore, so it probably shows a little less than 760 these days. But really, how this works is we have basically a pool of mercury, and we put this, in this case, it's a tube down into that pool. And that tube is sealed and it's under vacuum. And we're basically seeing how far up into this vacuum tube is the mercury actually getting pushed by the atmospheric pressure that's pushing down in the mercury-filled tube. The mercury-filled container here at the bottom. And so the atmospheric pressure pushing on the mercury here helps push mercury up the vacuum tube. And this height, regardless of how big or how wide or whatever the dimensions of your tube are, the height of mercury that it goes up should always be 760 millimeters, roughly, if you're at what we consider standard atmospheric pressure. And so that's where this measurement of 760 millimeters of mercury comes from, is from this, what we call mercury barometer. Again, there's probably slightly better updated versions of this. Even the one we have in Rogers does not have like a pool of mercury just sitting out, so don't worry, there's not a pool of mercury sitting around that anyone can inhale vapors off of or anything like that, because that would not be the most healthy thing for anyone. And so most things today probably going to be a little bit more evolved, but we still refer to them as barometers. And most of the time when we're measuring things, a lot of times you might even see even from weather stations today, like if you're looking at like weather forecasts and things like that, they might give you a pressure that's in inches of mercury instead of millimeters. because they still work off kind of a similar concept as far as that's just the standard unit so many people have used to measure pressure for so long that it's still very commonly used even today. Something else that can be useful for measuring pressure, it's a little bit harder to maybe get the exact pressure, but in terms of finding relative pressures, it is pretty useful. Something called an open-end manometer. And so what you see here, we have these U-shaped tubes here, and you have kind of a dense liquid. It can be mercury or it can be a different liquid. It doesn't really matter. The more dense the liquid, probably the better it is to be able to kind of see these differences. But usually what happens if you have a liquid in this U-shaped tube, if you have a gas that's in a reaction container over here and then atmospheric pressure opened on one end of your tube, what's going to happen is the pressure from one of these directions is going to be higher than the other, right? So if the pressure here, the atmospheric pressure, is bigger than what's coming out of the flask, we're going to see the liquid that's in the U-shaped part actually get pushed more towards, in this case, the gas. This means the gas has less pressure coming out of it than the atmospheric pressure that's pushing down from this side. That's why we see it kind of pushed this direction. The atmospheric pressure is effectively bigger. That's why it pushes it kind of the other way. Likewise, if the pressure inside the flask is bigger than atmospheric pressure or 1 atmosphere, then you'll typically see the liquid get pushed towards kind of the open end instead. And so this, if you're doing a reaction in a container and you're just curious roughly what the pressure is, like, relative to 1 atmosphere, is it bigger or smaller? This is kind of a quick way of being able to test that as far as kind of an application. All right, so I think that's enough kind of quick background and introduction to pressure as far as kind of it is one of the main physical properties of gases that we often talk about and can measure. Turns out there's really 4 different properties of gases that we often are going to talk about that are all going to show up in this chapter. And when you have kind of pairs of them, we'll have what we call individual gas laws, and eventually we'll have an overall ideal gas law that involves all of these properties. But these 4 properties that we're going to talk about for gases are going to be the pressure that we've already talked about. We'll have temperature, right, which temperature we've used a bunch this semester. And then we're going to have volumes, basically just the volumes of your containers. And then the last one's actually going to be the number of moles of gas that are actually present in a particular container. So these are kind of the 4 measurable physical properties that we often talk about for gases in terms of being able to do calculations and really being able to then do kind of stoichiometric calculations for gases as well. So for instance, we've done a bunch of stoichiometry problems previously this semester for solids and for liquids. Well, once we get through kind of some of these gas laws we're about to talk about, especially the ideal gas law, we'll actually have a way now to be able to talk about doing stoichiometry for gases potentially as well. And we'll look at an example problem with that here today too. And in terms of putting all of these things together, there's a bunch of individual gas laws that relate kind of each one of these variables to another. And I'm going to show 3 of them right now. There are some others, like for instance, like the Gay-Lussac law is also another one that's sometimes shown in textbooks that we are not going to cover, that I'm not going to cover right here. Because really, you only need 3 of the individual gas laws total to be able to put them all together to see an overall we call ideal gas law. And that's what I'm going to kind of work our way towards. So how I'm going to do this, I'm going to look at kind of some of the most common individual gas laws and look at kind of what measurements do they compare or try to relate to one another. And we can think about these 2, hopefully just conceptually first, and then I'll kind of show the relationships, just kind of verify things. But the first one to take a look at is called Boyle's law, which is a relationship between pressure and volume. So one of the ways to think about this, if you have a closed system that is basically isolated from everything else, and if you take that system and you change the volume, but you keep the amount of contents in that system or container, you keep the temperature inside of it and the moles inside of it all the same, then you should see a change in pressure as a result of that, right? And so pressure and volume in terms of how they're comparing, if you make your container smaller, and we'll talk more about this in our next lecture too from kind of what we call a kinetic molecular standpoint, but if your container gets smaller, and you think about, pressure is all of the collisions that are caused by all the collisions that are happening. The smaller your container, the more collisions there are. The more collisions, the more force is being provided. So there should be a larger pressure as a result. And so smaller volumes, which will be a smaller container, should give bigger pressures, meaning these things are kind of oppositely related. And that's exactly what we see. And so they're what we call inversely related to each other. So if moles and temperature are constant, changing volume will then change the pressure by really the same amount. So here we see kind of a visual example of this over here. So if we have a volume of 1 liter and we have an atmospheric pressure pushing down at 1 atmosphere of pressure, Those things, like if we adjust one, it's going to adjust the other, or vice versa. So here we doubled the pressure that we're pushing down on this little piston with. So doubling from 1 atmosphere pressure to 2, the volume goes from 1 liter to 0.5. Right? Pressure doubled, volume gets halved. We'll always see kind of that exact inverse relationship between these two physical properties. And so this leads us to something called what we often refer to as Boyle's law, which is basically that pressure times the volume should be equal to some constant value if our moles and temperature are not changing, right? The moles of the gas in the container and then the temperature, average temperature of everything inside of it. And this can lead to really kind of just a simple equation here. It looks similar to what we did for dilutions earlier this semester. We had like M1V1 equals M2V2. Here we have PV, or basically it'd be like P1V1 equals P2V2 would be another way to think about this. It'd be pressures and volumes, right, instead of molarities and volumes, kind of working through a similar idea. So this is one relationship out of those relating kind of those properties that we saw before. So another one is going to be what we call Charles' law that looks at temperature and volume. This is actually the lab we'll be doing next week. That'll be sending out a video probably in the next couple days as far as kind of what's going to be happening with it. And what we're going to see for Charles' law is we compare volume and temperature. And if you think about maybe some real life examples of this, like a good one for this, like if you play sports and are used to having like a basketball or a football or something like that, and you go outside and it's really, really cold, what happens? Well, usually that ball deflates. And if you have a balloon, you can kind of see the same thing. If you have a balloon, you go outside and it's really cold, the balloon will deflate a little bit. And vice versa, if you go somewhere that's really hot, it will basically expand some. So volume and temperature, if temperature as it goes down, if the volume then decreases for things to deflate, or vice versa, as temperature goes up, things expand, these are what we call then just directly related. Right? As one goes up, the other goes up, and it should be pretty much even in how that happens. Now, one thing I'll point out though, and you'll see this from the image I have over here, the temperatures that you care about aren't going to be temperatures in Celsius or Fahrenheit, they have to be in Kelvin. So for instance, if we want to heat a container enough to double the volume of something, we're not going to take it from like 10 degrees Celsius to 20 degrees Celsius. Even though that's doubling that temperature, it's not the right scale. It has to be a Kelvin temperature that's doubling, right? So in here, if we have 0.5 liters for our volume inside this container at 200 Kelvin, if we want to keep the external pressure the same and the contents, the number of moles inside the container is the same, in order to get to a volume of 1 liter, which is twice as much, that temperature has to double in units of Kelvin. So it goes from 200 to 400 Kelvin for that temperature change. So something to kind of keep in mind, temperature, anytime we're using temperature for any of this gas law stuff, has to be in Kelvin. And that should probably be a pretty common thing at this point that you're probably used to. If you're using temperature in a calculation as just that temperature, it has to be Kelvin for everything that we see. Kind of the only time we can get away with using degrees Celsius for something is if we end up doing like a difference in temperature. So when you have like the heat equations or the Q equals MC delta T, like delta T's you can leave in Celsius because Celsius or Kelvin, the change in temperature is the same either way, it doesn't matter. But otherwise, if you have to use the actual temperature at any point in a calculation, it has to be in Kelvin for any of these things we're doing. That applies to really this semester in 1211 and kind of future semesters in 1212 and beyond as well. And what you'll see then kind of in the Charles Law lab that you guys do next week as well, or kind of observe next week, we can basically take the volume over the temperature as a ratio, right? Because if these two things are directly related, if we imagine putting them on the same side of the equation, if I have to divide this over, that's why like this volume over temperature is going to be some constant, or like V1 over T1 should equal V2 over T2 as a ratio. And this is really what we'll be doing next week in lab. We're basically just going to try to measure volume and temperature at two different like points, like at a hot temperature and a cold temperature. We can measure the volume at those points and then just try to observe like, all right, do we get about the same ratio for each? Do we get a ratio that makes sense? Right. The third individual gas law we're going to take a look at is Avogadro's law. Like I said, some places might look at Gay-Lussac's law as the third law, which would basically just be taking a look at like moles and like temperature instead, or even like other things like Dalton partial pressures, like moles and pressures as well. But this one works just fine. Avogadro's law, looking at volume versus number of moles of gas, which hopefully should make sense, right? If you've ever tried to blow up a balloon, what do? You have to blow air into it. Right? So as you blow air in, you're adding moles of air, and what happens? The balloon expands, right? And so I think this one, hopefully, again, also fairly intuitive. As our number of moles of something increases in our container, if the pressure is constant and the temperature is constant, then the volume should go up, right? Just as much. So for instance, if here's what we're starting off, we have 1 mole of gas with a 1 atmosphere external pressure. If that volume is 22.4 liters, if we had a second mole of gas, we have 2 moles of gas in the container. If the temperature is still the same and that external pressure is still the same, the volume should now be twice as much as well. Right? So they're directly related, which means it's just like the Charles law in terms of any kind of relationships. We can do basically the volume over the number of moles should be equal to some constant. Or we could say like, V1 over N1 equals V2 over N2 as far as like volume in the moles kind of comparison between those. Now, ideally then what we do with all of this is that we kind of put it all together, right? So what we're going to do, if we think about like volume is directly related to moles, it's directly related to temperature, but it's indirectly related to pressure. Well, that really means that we can get an equation that's pressure and volume on the same side of an equation with moles and temperature on the other side. And if we just know the proportionality, that means there's probably some constant that's also involved in this calculation. And that is what we end up seeing for our overall, what we call ideal gas law. So the ideal gas law is the combination of all 4 of those physical properties we talked about before, pressure, volume, moles, and temperature, put into one single equation, where the pressure of a gas times the volume of the gas should be equal to the moles, which is this N, times R, which is going to be the ideal gas constant that I'll talk about in a second, times then the temperature. Right? And so for all of these, the ideal gas constant does have a specific value that we'll pretty much always use in this equation. And this is 0.08206 liter atmospheres over mole Kelvin for the units. And I give those units because those units are extremely important. There's actually a second value for R that you will sometimes see that we don't really use much this semester. It might come up a little bit here at the end of the chapter, but then it gets used heavily in 1212 is the other version of this constant. But the only difference is the other version of constant just has different units. Instead of liter atmospheres, we'll have like joules. Here what we want to pick out is the fact that if we have liter atmospheres in the numerator, that's basically telling us that our pressure needs to be in atmospheres, the volume needs to be in liters, and we have moles and we have Kelvin. Notice if this is Kelvin, that means the temperature has to be in Kelvin to use this equation. If we put any of the temperatures, the moles, the volume, or the pressure with other units, this equation will not work with this constant. So kind of be aware of that and always know for this equation, pressure in atmospheres, volume in liters, temperature in Kelvin. Just kind of always be keeping that in mind. All right, so for using this then, I want to work a couple examples. So I'm going to take a look. We're going to give you a minute to kind of write down this first one. Or you can pause the video here and write down this first example. But I'm going to switch to my whiteboard here to kind of show it here in just a second. But what we're going to be trying to figure out is how many grams of hydrogen gas would need to be added to a 2.50 liter, flask, at a temperature of 25 degrees Celsius in order to create a pressure of 0.35 atmospheres if H2 is the only compound inside the container. So a couple things here. Any problem kind of here at the end of the semester or like on your final exam, whatever you see at the end of the semester as well. If you see things that have like a volume and a temperature and a pressure all involved, probably it's an ideal gas type problem. If you're looking for, or if they give you like a mass and like a volume and a temperature and ask you to find a pressure, things like that, it's probably the ideal gas law. So you're basically checking like, all right, in order to use the ideal gas law, which is that PV equals nRT, and I'm going to zoom out here now and let myself kind of work on some whiteboard space. So in order to use that ideal gas law, I want to be able to use PV equals nRT. If they give you 3 of the 4 variables in this equation, R is a constant, so there's only the 4 variables, right? PV, N, and T. If they give you 3 of the 4, this is pretty much the equation you need to solve the 4th one, right? That should be kind of the major clue you're probably always looking for. In this particular problem that we've started with here, we're looking for a mass, which is not in that ideal gas equation, but one of the pieces is moles. If we find moles, we can find mass with molar mass. But we do have a volume and a pressure and a temperature, which means we have all the pieces to use this equation to find N, right? And they do give us the ideal gas constant in the problem here as well. The units probably should be there. So if basically how I'm going to go through solving this problem, I'm going to solve this equation for N because I have everything else in this equation. And once I have my moles, to get to grams should be kind of good review for things earlier this semester, right? To go from moles to grams is just using molar mass. So if I solve this equation for N, my N should be PV over RT, right? And then I just want to put in my pieces. right? My pressure looks like 0.35 atmospheres. The volume is 2.5 liters. So 0.35 atmospheres times 2.50 liters, all divided by the R that they gave us, which was I'll put the 0 in here, 0.08206, and its units are liter atmospheres over mole Kelvin, times our temperature, right, which they say is 25 degrees Celsius, but we do want to put that into Kelvin, right? So you're adding 273 to that 25, which should give you 298. And now we have all of our pieces here. This should be able to help us find the moles that we expect to get, which I believe is somewhere around like 0.35 or so, if I remember right. Maybe 0.036 even moles of our gas. In this case, moles of H2 in particular, because that's our gas. And so this number, if we calculate this, this should be what we come out to. And actually, I think I've messed up a decimal place on this, so let me back up. I think this is actually 0.036 moles of hydrogen. There we go. That looks better. That we should be getting to. And now for the rest of this problem, we were asked for the mass, right? We want to know what was the grams of H2 that we needed. Well, in this case, if we want the grams of H2, I can take 0.036 moles of H2 times, right? I want grams over moles as my conversion, which is really just our molar mass, so 2.016 grams of H2 per mole. And I'm going to get somewhere about 0.07, oops, losing a 0 here again, 0.072 grams of hydrogen gas. Right, so that would be our final answer that we're getting to. And so something you'll see a lot of in these gas law problems, and I'll actually work a longer example with stoichiometry in a moment. You will see stoichiometry things linked to the ideal gas law pretty easily or pretty commonly. All right. The other example I had here, also very similar. So here we have 15 grams of nitrogen gas is added to a 2-liter flask at a temperature of 35 degrees Celsius. We want to know what pressure will exist in the flask. So same general idea for a setup here. So I'm going to scroll down a little bit here to give myself some space on my whiteboard. Notice in the problem, I have a volume, I have a mass, and I have a temperature. Well, mass can be very easily converted into moles if we know what it is, nitrogen gas, we can do that. So we basically have moles, temperature, and volume, which means in terms of the ideal gas equation, right, if I'm putting out that PV equals nRT, I have everything except the pressure, which is what I'm looking for. So I can rearrange this equation for pressure, right? Pressure is nRT over the volume. So in this case, my pressure should be equal to my number of moles, which I do have to do a little bit of work to find the N, right? Because they told me in my problem here, I have 15 grams of nitrogen gas. And one other thing I will point out here, you do for this chapter probably really want to remember your standard states for a lot of your elements, right? Nitrogen gas, nitrogen standard state is N2. Right, when we talked about standard states before, the diatomic elements were hydrogen and kind of that upside down L in the upper right corner from like nitrogen over to fluorine and down. And so nitrogen is one of those elements. It is diatomic, like something like an ACS exam, which we are going to have a modified version of for our final still. It will probably expect you to know that nitrogen gas is N2 in terms of like problems like this for the gas law type problems. So something to kind of maybe keep in mind. So here, in this case, nitrogen gas is N2. So in order to find our moles, we're going to take that 15 grams, and I'll just show it over here, right? N's going to be 15 grams of N2. I'm just going to write it as divided by its molar mass, right? Which you can write it with this, the normal kind of dimensional analysis way if that makes more sense still. But you're effectively dividing by molar mass, which for N2 is about 28.02 grams per mole. Which gives us about 0.535 moles of N2. All right, and so then for our pressure here, if I go back and put that in, I'll have 0.535 moles times R, which was that constant 0.08206 liter atmospheres over mole Kelvin, times our temperature, which they told us was 35 degrees Celsius. So again, add 273 to get to Kelvin, which will be 308 this time. All divided by our volume. And our volume in this case is 2.0 liters. That was what was given to us in the problem. And now again, all of our pieces are here. Notice our units, and same applies to the previous example as well. Like the moles can cancel, the liters can cancel, the Kelvin cancel, and we just have atmospheres, which is our pressure unit. So that is what we want. And if we calculate this, I believe this comes out somewhere about 6.8 atmospheres for a final pressure. So that would be our, again, kind of our setup for working through this. Most of these, not very hard, just as long as you pay close attention to the units. That's probably the big thing. But you'll also see some other types of problems with kind of gas laws in terms of how they're used. A lot of times it might not be just this one step of, solve the ideal gas equation as like really the only important part of the problem. So to show kind of a pretty common way these gas laws get applied is to take a look at how they apply with stoichiometry. And so I'm going to take a look at one more example, and I will work this one on the whiteboard as well, but I want to leave the actual problem up here for you to be able to read and write anything down, at least initially. And so they tell us here that we have a reaction that's used in the deployment of automobile airbags is the high temperature decomposition of sodium azide, NaN3, to produce nitrogen gas. And it asks us how many liters of N2 at 1.15 atmospheres of pressure and 30.0 degrees Celsius are produced by decomposing 45.0 grams of sodium azide. So, how does this happen? Or how do we go about solving this problem? Well, there's kind of two parts to this problem. We have a temperature, a pressure, and really a mass. We're looking for a volume, but we have to be very careful about something, right? We're looking for a volume of N2, and the mass we have is not for N2, it's of sodium azide. Right, so we actually have something we have to do before we can try to use an ideal gas equation that'll have the moles for N2, and that's really what we need to find. We need to figure out how many moles of nitrogen gas should we be making in this reaction so that we can plug that into an ideal gas equation with the temperature and the pressure they give us to find the volume. So to know the moles of N2, we have to actually basically kind of go back to what we would do earlier this semester, like in chapter 3 with stoichiometry, and then look at, all right, so here we have 45.0 grams of sodium azide, right? So we have a mass of how much reactant we're starting with, and we're interested in how much product we should make, right? And we're interested in the moles in particular. All right, so for setting that up then, I'm gonna go back to the whiteboard. I'm gonna try to leave this over here so we can still see the balanced equation mostly over in the corner. And so if we go and look at this, we're gonna take a quick look for setting up the stoichiometry. Right, we have 45.0 grams of the sodium azide, which is NaN3. And so the very first thing we're going to have to do is convert this into moles instead of grams. That's the first step of all stoichiometry problems. And so when we're dividing by, we're effectively going to be dividing by molar mass to have grams on bottom, moles on top. And so our mass for sodium azide, let's see, what would that be? Probably going to be pretty close to about 65 grams per mole, if I remember right, for those masses. So 45 grams divided by 65 grams times, here we're going to get a ratio. And so this ratio, our end goal is to find the moles of N2, right? That's the gas that we're producing we want to eventually find a volume for. And we're canceling out our moles of the sodium azide, the NaN3. And this mole to mole ratio, remember, is just what comes from the balanced reaction. So we should be making 3 moles of N2 for every 2 moles of the sodium azide that react. Right, so there's our stoichiometric ratio. And again, hopefully those steps look familiar. We don't have a last step that we have to do here. Right, this just is the full number of steps that we're actually going to have to do. And then we can go through and really actually just divide all of this out, actually see kind of what this all comes out to. And so if we do that, let me actually, I think I have the value here on this next slide. If I click back to the slides. Oops. Right, and so it looks like it comes out to, if we multiply by the 3/2, right about 1.04 moles. Oops. I'm writing this on the whiteboard that I'll go back to in just a second. So we have about 1.04 moles of N2 based on the stoichiometry. Now we can go back to the ideal gas law, right? And I'll show this on the whiteboard side just to finish this up too, right? So we're looking for a volume. If I rearrange that pressure equation, it's going to be nRT over P, right? Rearranging the ideal gas law, which for putting our pieces in will be 1.04 moles of N2 times the constant, 0.08206 liter atmospheres over mole Kelvin. The temperature was 30 degrees Celsius, which into Kelvin is going to be 303, all divided by our pressure that they gave us, which they told us was going to be 1.15 atmospheres. And I'm going to break things here if I can, just to kind of know that the 1.04 moles of N2 is what we got from that previous line, right? And then the answer here for our volume that we're finally trying to solve for should be what I had in the slide here, which comes out to about 22.5 liters at the end of this. So this is a really big volume, right? If you think about like the size of like a 2-liter bottle of soda, this is 11 of those in terms of size. So that's a big volume from about 45 grams of material that we're decomposing, which is not a ton of material. So not a really big solid amount of stuff that we're reacting, but we're getting a huge amount of gas, which is why this stuff gets used for airbags, because you can have a little tiny quantity to inflate that airbag that you would have in a car. All right, so I think that wraps up that example. I have one more kind of last general thing from a kind of a calculation sense that we're going to talk about here in this chapter. And so we're going to take a look at that calculation. We're going to take a look at what we call Dalton's law of partial pressures, and we'll look at one example problem dealing with it as well. And then we'll look at, then we'll wrap up for this part of kind of the first part of chapter 10. So Dalton's law of partial pressures. What this really kind of tells us is that ideal gas law, one of the things you'll notice about it, there's nowhere in that equation that has anything to do with what the identity of the gas is. And so basically that's kind of a useful thing to know. And it basically means that the pressure of a gas only depends on how much is there and not on the gas, like what it is itself. And that's a really big idea kind of conceptually to understand that the size of the gas, the molar mass of the gas, that kind of stuff doesn't matter for pressure, right? Pressure only really depends in terms of the gas, how many moles of it are there. That's the biggest thing that matters. And so this applies then if you have lots of gases all mixed together. The only thing that really matters to the total pressure of your whole system is just what's the total number of moles. And you can treat each of them individually. And so you can actually find the pressure of each gas individually and just add them all up. And you can find these pressures by using things like the ideal gas law, even potentially, which will kind of be what we look at in the next example. Or you could just figure out like what's the total moles of all my gases and then figure out the pressure total from that. Your total pressure is just the sum of all the pressures of each gas kind of on its own, and you can calculate them each on their own if you have problems where you need to do that. So I think this is maybe best demonstrated kind of in our next example that I'm going to take a look at. But again, the big thing here is just like each gas or each component of a mixture can have its own pressure that isn't affected by what else is there. Like it doesn't care what other things are there. Each gas is going to have its own pressure just based on the number of moles it has. And you can sum all of those individual pressures for each gas to get your total pressure for the whole thing. And so that's what we kind of want to keep in mind as we kind of take a look at this example. And so here we have a 10.0 liter vessel that contains 12.45 grams of H2, 60.67 grams of N2, and 2.38 grams of ammonia. And we're asked, what is the total pressure of the mixture at 90 degrees Celsius? So we're looking for the total pressure of everything. We have amounts of each individual gas. So we have a couple options on how we do this, but the first thing that we're going to have to do is still the same for all of them, right? In order for us to use an ideal gas equation, which is temperature, volume, we're looking for a pressure in this case. That means we need the moles. What we have here are masses. So the first thing that we have to do no matter what is change all of those masses into moles. I'm actually going to show this on the slide just because I have this part here, right? So for H2, right, we can divide its mass, the 12.45 grams that we have, by its molar mass of roughly 2.012 or 2.016 if you want. Probably this should be like 6.18 moles of H2 for being careful with sig figs. And then for N2, we had 60.67 grams of nitrogen gas from the previous slide. Divide it by its molar mass for N2, which is about 28.02 grams per mole. We have about 2.165 moles of N2. And then we have ammonia, NH3, which we had 2.338 grams of. Divide by its molar mass, about 17.03. And it's only about 0.140 moles of ammonia. All right, so from here, we have two different options on how to get to a total pressure. In this slide, I'm going to show you how you can find each pressure individually. And then on the whiteboard, I'll kind of show the alternate route, which is just getting the total moles, and then from there, actually getting the pressure. So if we want to solve, basically, we can, for each of these, like for H2, if we know there's 6.176 moles of H2, what we can do is actually use the ideal gas equation to find the pressure of just H2, right? And so I can show that here in the next slide. So for H2, we can take its moles, ideal gas constant, there's the temperature we're at over the volume. It's about 18.4 atmospheres of pressure from just hydrogen in that container. I apologize if you hear pounding of rain outside. It's a little bit stormy at the moment as I'm recording. But for nitrogen, what we're looking at for nitrogen, same idea, just the ideal gas equation. The only thing that's different is the moles, right? Constant, temperature, volume, all the same. So for nitrogen, putting the right number of moles, you got about 6.45 atmospheres. Same for ammonia, fewer moles yet, so about 0.417 atmospheres. And at the end of all of this, if we want the total pressure, all we have to do is just add all the individual pressures together, right? So we have a pressure for each gas that we can go through and just combine, and we get a total pressure of about 25.3 atmospheres. But there was another option on how to do this, and I'll leave this here. And if you want to pause it here to write this down, that's fine. I'm just going to kind of minimize back down to the my kind of whiteboard screen view of things here real quick. And what this whiteboard screen view I'm going to show is that we can use the total moles as well, right? So for instance, from this problem, if I come over here and slide this over some, I'm going to slide this over enough where I can see, hopefully the moles is what I really care about. Because the other option I have here is I can do a single PV equals nRT equation, but I just want to find what's my total number of moles, right? So in total, if I add all these up, right, I have 6.176 moles of H2 plus 2.165 moles of N2 plus 0.140 moles of ammonia. Right, and so if I add all these up, give me a second here as I go through and add all these up. It's like 8.481 roughly moles total. I can now use that for my N in my ideal gas equation to find my pressure. So 8.481 moles of, it's not moles of any particular compound, it's now just our total moles, times R, ideal gas constant, times our temperature, which they told us, which in the problem we said was 363 Kelvin, right, 90 degrees Celsius, all divided by our volume, which was 10 liters. Now we can calculate this pressure. If we calculate all of this, it should come out to the exact same 25.3 atmospheres that we had previously. So we do get a couple options on how to get to that final total pressure if you want to do each gas by itself and then do it. Or probably the faster way is if you just know the total moles. It doesn't matter how much of each one you have. If you just know the total moles of gas in a container, you can find its pressure. Unless you're at some kind of extreme circumstance, which is some of the things that we'll be getting into in the second part of our Chapter 10 lecture that we'll talk about next time. And so this is actually all I have for the first part of the Chapter 10 kind of material. This is the more calculation-heavy side, although there are some equations and relationships that we'll take a look at in the second part as well, that will relate some other things and properties of gases. But the next part will really be taking kind of a molecular level picture of things as far as like what's really causing pressure and really trying to make better sense of how really all of these properties are related in the ideal gas law and kind of where that relation or where those relationships come from. So that hopefully that makes a little bit better sense. We'll also talk about some kind of relationships with pressure, and also then start talking about that even though for this equation the identity of the gas doesn't matter, but if we want to start finding things like how fast are the gas particles moving and things like that, now the identity of the gas does actually matter. And we'll take a look at kind of some of those relationships and something called diffusion as well. And the last thing we'll probably touch on to wrap up the chapter will be the exceptions to this ideal gas law. Because there are some times where this equation maybe doesn't work very well, but you do have to be at really extreme conditions. If you're just in a normal everyday lab like our Gen Chem labs or organic labs, this equation is always going to work. We're not going to have extreme enough conditions for it to really fall apart. If you're working under some really specific conditions, though, with extreme temperatures or pressures, it's possible that maybe then we actually start having to consider how to correct for some of the assumptions that are made to use this equation. And that'll, like I said, that'll be kind of the last things that we'll wrap up with next time. Right? But that's all I have for now, and I will see everyone then here in a couple days for our last lecture.